Hello there, I'm Brás, a computer science doctoral student at the Federal University of Pelotas in Brazil, and I'm here today to talk about GrameStation, specifying games with graphs. Computer science education has evolved and changed throughout the years. It has been less and less common that idea of teaching code right away. What is on the rise nowadays is problem solving. Much said about computational thinking, an expression the scientist Janet Wing brought back to discussion in 2006. It refers to a set of skills related to computer science that help us with that problem-solving process. We can get some clues of why these things have gotten stronger in the field if we look at problems that used to be there, and actually still are, in the teaching and learning of programming. Among the challenges the students face, we have things like the problem formulation itself, to understand and conceptualize the problem that is being dealt with, the abstraction that is required to understand concepts such as variables, data types, and memory addresses, the algorithmic thinking required to sort the thoughts out in a systematic and well-defined way, the way that the machine that is going to execute it works, and the language syntax that may bring a cognitive overload if you try to learn it while solving the problem at the same time. We can see that even the programming languages advanced their generations trying to tackle those challenges. The lower the level of the language, the lower the abstraction, and the higher the concerns about the syntax. More specific the problem formulation must be, and so does the algorithms to solve it. That is why, especially in education, the languages have been easing the syntax and keeping the level of abstraction higher, using resources such as the block programming of Scratch, for instance. But the truth is, the root of the problem is to start coding before even knowing what is going to be coded. Trying to understand the problem while already implementing its solution, even though no solutions were found yet. If we are not to run everything over, there is a stage that precedes implementation, the specification, wherein we properly face the problem, where we are going to stop and think about what we have, what we need, what should happen, what should not, and overall, what could be done. Therefore, our proposal is an effort to proceed with things the literature has shown that works, such as the visual language to ease the syntax, game-related environments to keep the motivation, and active learning methodologies to place the students as protagonists of their knowledge, and bring it all to a specification-centered approach, for which we rely on graph-grammars, a formal specification language that we directed towards game creation, games as graphs, graph games, which we are naming Grames. And to follow the trends of active learning and maker culture, we built a gaming guide where the students can create and share these Grames, the GrameStation. That graph-grammar is a mathematical formalism to specify and verify systems. It describes the systems using graphs to represent the states of it, graph transformation rules to represent changes of state, and types to differ and restrict the vertices and edges used in the graphs. It is like one of these Chomsky's generative grammars that are used in lexical analysis, but with graphs instead of words. The cool thing is that to build a game in GrameStation, you basically just specify a graph grammar. The only additional thing you have to do is to manage the packages of resources. But that's nothing scary. They are just external files as images and sounds that you import into your game. And actually, this should be your very first step, to think, what is my game going to look like? The second step is to think, what kind of things are going to be featured in my game? What are going to be the characters, the objects, and more importantly, because it's a graph, how is the relationship between these things? Example, for the Pac-Man game, we need to feature the Pac-Man, ghosts, fruits, places where they pass through, and thus all of them must at least stand in relation with the place they are at, because being there is a relation itself. Once you know what the game features, it is time to think, how does my game start? Think about how you are going to build the first phase. How many places is going to be there? Where will the Pac-Man come from? What about the ghosts and the fruits? How are all things going to be when you open the game? At last, you need to think, what could happen in my game? The Pac-Man should be able to move from a place to another, so does the ghosts. The Pac-Man should be able to eat the fruit, the ghost should be able to kill the Pac-Man. But how can you do all of that happen in a graph-gramar? Basically, you need to think, for each of those events, how was the situation before it happening and how it is going to be after it happens. This before part is the left-hand side, where you must think what are the necessary conditions and build a graph that represents it. Here, on the right-hand side, you must think what are the consequences, and again, build a graph that represents it. So, this rule here, for instance, says that the Pac-Man must be in a place that has a way to a second place so he can move to the ladder. That all was about creating games. Now, to play the game, you have to select a rule and find a match for it. That is, to map each of the elements of the left-hand side into an element of the current state of the game. You map, apply the rule, and then it is time for the next player to do that. In order to help the students to build graphs, we've implemented a decision tree system that guides the user, asking them what are the properties of what they want to do, already offering all correct options available. They just need to choose. Beyond all the focus on specification, some characteristics of graph-gramars can be related to computational thinking skills. The abstraction level is pretty high. It is a parallel declarative language and it doesn't even have a textual syntax. Instead, a computer science well-known data structure is used, graphs. The execution is all based on pattern recognition and you can't make a single play without analyzing the current state, due to the match being mandatory for rule applications. Thus, what we bring is an effort to spread an approach around problem solving that tries to rescue the specification stage that has been long neglected. For that, we use a graph-based visual language to make games while fostering computational thinking skills, resulting in the creation of GrameStation, a graph-gramar game engine. We intend to finish several other works continuing this one, mostly for validation of user experience, target knowledge, computational thinking skills, and all of this shall be tested on both students and teachers. We already have a work in progress to bring pedagogical agents to the GrameStation, helping new users. And later, we want to verify if we are able to predict learning outcomes using the data that the engine captures while games are being played or made. And that's all. Thank you very much, and I'm open for questions in the comments or by email badsjunior@inf.ufbel.edu.br.